This is a joint work with my colleague of my lab in Belgium and ETH Zürich with Laurent Vanbever and ING with Randy Bush. So before going to xBGP, a little bit of context. In traditional routing, you have a router from different vendors, and this is a best practice, in fact, for economical reason and for stability reason. So, for example, imagine you have a bug in one network operating system. There is a large chance that all operating systems have the same bug. And because of this plurality of vendors, all the routers do not implement the same set of functionalities. And this is a major problem to evolving your network. Because, as you may know, networks are rapidly evolving, and they constantly tune their network to actually offer a better service in their customers, but they are limited. First one, because vendors implement their routers as a black box, and you cannot interact as much as you can with this interface. And the second one is because BGP is a standard for question of interoperability. It's in between different vendors. You need to discuss them within the ITF. So one example of interesting feature for operator is the following. Imagine you have intra-routers in your network that prefer European routes for whatever reason, but with the actual implementation of BGP, there is no information about the exit router. So what we would like to have is a kind of tag to actually discriminate the exit routers so that it can actually compute what is his best route according to his routing policies. This one is actually a draft, as I said, and the draft stipulates that you need to, each time you you receive a BGP update, add your latitude and longitude of the routers who receive the routes. Then you spread your new attribute inside your routers, and to avoid polluting the internet with the new attribute, you need to remove the geographical localization of your routers before spreading it into other BGP neighbors. So this is complicated to achieve with classical routers because this requires to have access to the BGP implementation actually. And this is really complex because you cannot ask to your router vendors to actually implement it. So the first step is to pass to the standardization phase within the ITF. And on the slide, you have the standardization delay of multiple functionality of BGP throughout the release of BGP protocol implementation. And actually, it takes roughly 4 years to have it implemented as the standard. This is confirmed by another study. You can check the paper if you are interested. And then once the standardization phase is done, you have to implement it into your Bonaventure OS and then update your routers. But if you are a small network ISP, such as Belnet, research network in Belgium, you cannot easily influence step 1 and step 2 because maybe IETF people have no value on your functionality, or even your router vendors will not add the functionality because you don't have the required license. So let us resume the problem now. You have major problem. The first one is that you have routers from different vendors. You have protocol extensions that are not implemented on all routers, and you have the slow upgrade process. And xBGP is intended to bring back innovation and programmability inside existing routing protocols. So let's start to explain what is xBGP. So if I take back my GeoLoc feature, it actually needs to alter the BGP workflow, and the BGP workflow is normally implemented on all vendor operating system, and this is the RFC 4271. And it stipulates that each time you receive a BGP message from your peer, you go to the edge ribbon, then import filter, the log grep, then the BGP decision process that will compute the best route toward each IP prefixes. Then you have to pass it to the export filters, edge reroute, and then spread it to the other BGP speakers. So with the actual interface of network operating vendors, you cannot access to this BGP workflow because you have some interfaces such as CLI, netconf, or SNMP for monitoring. And xBGP is intended to open this black box to expose the BGP workflow on the routers. And this is done via adding a new interface, xBGP, that will take the code that the network operator will write itself, then executing in the VM on the corresponding place of the BGP workflow. So if I take back my geographical localization extension, this must be added in several parts of the BGP workflow. And actually, in xBGP, we call the green circle insertion point. This is a place where you can actually execute code provided by the operator. And this GeoLoc attribute will actually be divided in subparts. So decoding, add it, use it, delete it, and encode it. And those subparts will be added on the several parts of the insertion point of the BGP workflow and executed by the VM. So now operators have a way to implement its own extension, then push it on all routers that is xBGP compatible, and then you have your new extension all on your network. And I said that xBGP is using a VM, sorry. Actually, it is eBPF for its mature tooling, compiler, debugging, and so on. So you can think that xBGP is a common layer between what the operator is writing and what the network operating system is implementing, and it makes the link between two. And what is interesting with this approach is that you have actually multiple representation for the routing table, the memory, the network input-output, BGP state, and so on. And these are the only thing that change in this paradigm. And the network operator won't change its plugin between these router vendors. So to prove the programmability of xBGP, we added our interface in two open source implementation of BGP, which is FRRouting and BIRD. On the slide, you have some lines of code that we have to modify or edit to make it xBGP compliant. And throughout this presentation, I will explain the geographical location in use case, but actually to prove that xBGP is as generic as possible, we have implemented other use cases, and if you are interested by those, you can check the paper or the code itself. So we have now xBGP, but now the question is, does using xBGP have an impact on router performances? And to measure this impact, we are making a small experiment that we have a router of the left that will inject a full routing table on the internet to our xBGP routers. And actually, we measure the convergence time of our xBGP router. And the first thing to evaluate is what happens when there is no xBGP program that is inside the xBGP routers. Actually, there is a small overhead because you would need to build the environment to accept a new xBGP program, but this is really reasonable. And now we are wondering what if we implement a huge use case, for example, route reflection, what would happen to the router? And actually, we make the comparison between native code and xBGP implementation of route reflector, and the overhead is no more than 13%, which is really reasonable given the flexibility benefits. So there is a small difference between BIRD and FRRouting because actually the serialization process in FRRouting takes more time than in BIRD. And you have also other reasons. So, for example, the JIT compiler to make your eBPF bytecode into machine code is not efficient as you compile it in there directly inside the machine code. So yeah, now the operator have a way to write his own program, but does break the BGP implementation? Actually, maybe, because it could write a buggy extension code that could crash the routers. And to help this kind of problem, we have built a kind of verification framework that takes the source code of an extension that you need to annotate with some code, then pass it to several verification tools. Then if the verification tools actually say there is no problem with your extension, you have to compile it, and then you are ready to push it into your xBGP routers. So actually there is basic properties such as termination, memory safety, virtual machine isolation, IP restriction, and also the most important one, the properties related to BGP itself. And I will take an example with my GeoLoc extension. Actually, it is defined in the draft, and the draft stipulates that it must respect the TLV, so that all routers must speak actually the same language. And here you have a small header for this extension, and you need to annotate your program to actually respect those values. So for example, for the flags will be 8, the type code 2A, and so on. So this concludes my presentation. Thanks to xBGP, you have implementation that is truly extensible. You can check this QR code or the website in the slide for writing source code. And we have made this approach for the BGP protocol, but actually the methodology could be also applied on other routing protocols such as OSPF or ISIS. Thank you.